of HEALROAD. I mean, he will speak about, he will detail the study focusing on the different effects of the bitumen type, the different metal particles and content used, the type of asphalt mix used, the content of wrapper, the hygiene and durability. So, Brexo, please.
Thank you very much, Jose, for this introduction. Thank you, Dani, Professor Castro, for the introduction of the project. And I think I can talk on behalf not only of the University of Nottingham, but also on behalf of the rest of the partners to say thank you for the good coordination of the project. You made our work much easier, so thank you very much. Thank you to the organization of this symposium and this conference because for bringing me the opportunity of being here today. It's a pleasure for mainly two reasons. One is because it's an honor being addressed in such a nice audience. And another one is because after a long, long winter in UK, finally, at last, I could see the sun again. So that made me really happy, so thank you very much. I will talk during my presentation, as it was said before, about just the highlights, because I only have 15-20 minutes. So I will try to summarize the highlights of the findings of laboratory work. As Professor Castro introduced before, the technology is quite simple, the concept. So what we did was to introduce in conventional asphalt mixes, we introduced some metal particles that you can just leave embedded in the road. So after some years, due to traffic conditions and weather conditions, first cracks will appear. And at that moment, we can go with our induction coil, apply a variating electromagnetic field. So we are going to induce some microcurrents through these metal particles. As a consequence, these particles are going to heat. The embedding bitumen is going to heat as well, so its viscosity is going to reduce. This bitumen is going to expand and to flow through cracks. And as a consequence, we are going to heal these cracks. As soon as the road gets cold again, we will be able to open it to traffic again. I prepared this very simple video that I always show. So it's a very simple demonstrator I did in the lab to show you a bit how we work in the lab. So this is a sample of asphalt made with some particles of steel slag. As you might know, steel slag has metal inside, so it's going to have capacity to be heated by induction. So basically, I split the sample into halves. Then I put both halves together. I'm putting out this tape. It's not that the tape is applying any pressure or anything like that. It's more like just to prevent both halves to get separated during the process. And now I'm going to just place the whole sample under the induction coil. We will be able to see how it heats thanks to an infrared camera. So you can see without touching the material, just applying this variating electromagnetic field, we will be able to heat the material. You can see here very well where the metal particles are, and you can see how in less than 2 minutes we can reach temperatures above 100 degrees. Actually, if we leave time enough, we can even burn the bitumen. Of course, we don't want to go that far. I just did this for this demonstration, but just to demonstrate that the technology has a great potential to heat the material. So when the material cools down again, the material is resistant. So of course in the lab we don't work like that, just breaking samples at least not every day. We don't break samples with a hammer. On the contrary, we apply a load in a hydraulic press, and so we are going to register the maximum load that the sample can resist. So this is the ultimate load that the sample can resist. After that, we put both halves together, we apply a certain healing energy, and we're going to repeat the same process, obtaining a new ultimate strength. The ratio between both is what we call the healing ratio. So a healing ratio of 80% means that we have recovered, thanks to this healing process, we have recovered 80% of the initial strength. I think it's a very simple test, but we have it repeated. This is like our flagship test, and we have repeated so many times during this project. This is to assess the healing of a complete crack, but to assess the healing of fatigue micro cracks, what we did was also the 3-point bending conditions in prismatic samples, but now we are going to apply a cycle load without breaking the sample in just one load. And so we're going to take a series of samples, like 15, 20 samples. We're going to measure the number of cycles that they resist. To that, we are going to fit a Weibull statistical distribution, and we're going to take as a reference value the number of cycles that has the same probability, 50%, to break the sample or not to break the sample. So this is kind of getting the average number of cycles when the samples break. But in terms of fatigue, it's more accurate to talk in terms of wave distribution and not the average, but this number of cycles whose probability of breaking the sample is 50%. So let's imagine that now, if this is the normal material, so it's expected to break when at this number of cycles, this reference that I was talking before. If I apply at a certain number of cycles a healing process, the sample is going to last a bit more. So this extension of service life divided by the reference value is what we call the healing index, but now in terms of fatigue life. So it's like, so in this case, if the healing index is 30%, for example, we are saying that we are extending the service life 30%, respecting the reference fatigue life without any healing. So if now we represent, so if we apply different healing energy, we are going to obtain different healing levels. So each point of this is a different sample that was healed for a different time or with a different heating energy. So in this case, every color is, there are samples made with different types of bitumen in a range, the conventional range of bitumens that we usually use here. So from a penetration grade 40-60 to 70-100. And we try to correlate different properties of the bitumen, such as penetration grade, viscosity, density, thermal expansion, fractional distribution. So the results of SARA test, the asphalting content, maltings, and so on, FTIR, and capillary test. And this brings me, this example, brings me the first great conclusion that we could obtain in the lab. And is that none of these properties could be correlated to healing capacity, which is very interesting because it means that if in a real case I ran out of my bitumen, the bitumen that I'm using, and I just want to change to a different type of bitumen with a different penetration grade, viscosity, or whatever, the healing capacity is not going to be affected. And that's really convenient for us and is very interesting. We also know that so these points are different samples heated by a different time, and this is the temperature that they reached, and this is the healing that they reached. So we also know that as long as we increase the temperature, the healing also increases. But if we reach a steady state temperature, and we just keep that temperature for a long time, what we are doing is that we are damaging again the samples. So that's a problem. That's something that we have to take into account. There is an optimum heating time to heal the samples. Why this happened, we could see, as I show in this picture, you can see here a CT scan, same section, but when the crack was produced, then after the optimum heating time, and then after overheating the sample. What you see here is the same, so it's a 3D representation of the crack. What you see in gray is actually air, so here is the complete crack. After the optimum, the crack has practically disappeared, but then if I just overheat it, new air voids appear again. We can also see that this is how the sample looks when it's new, and after overheating it, this is the bottom side of the sample. You can see how the bottom sample looks very wet, very rich in bitumen, while the top side looks very dry. So you can see even the new cracks had happened here. So the explanation of this is that once we reach the steady state temperature, the forces, the complex combination of all forces happening in the sample, which involves hydraulic pressure, hydrostatic pressure, capillarity, gravity, thermal expansion, and so on, energy losses and so on. So they reach an equilibrium, and from that point onwards, the gravity just drags down the bitumen. So it's not convenient that we just heat and heat and heat the sample for a long time. Is what we are seeing here. One of the main disadvantages of this technology is that we have to add metal particles to the asphalt. So we are increasing cost and we are increasing the environmental impact. So one way to reduce this is to use byproducts or waste products. In this project, we used 4 different types of samples of metal particles. 2 of them, the 2 on top, are commercial products. So it's a steel grit, which is kind of an aggregate, metal aggregate, rounded, and a steel wool. And 2 byproducts or waste products, which are fibers from old tires and shavings from metal industry. In general, when we compare the properties of the asphalt with asphalt without any metal, we can see that both volumetric and mechanical properties are not actually significantly affected. Some of them, they are even improved, and the only case that could say that is significantly worse is the resistance to water damage when we use the steel grit. The steel grit is like a very strong aggregate, so it's going to behave very well mechanically, but when it comes to the stripping resistance, so the adhesion between the metal and the bitumen is not as good as a conventional aggregate, so the resistance to water damage is going to be worse. For this reason, we recommend to use this type of metal particles in bottom layers that are more protected from water. Similar thing happened with the tire fibers, because what they presented is a really, really good capacity for heating. They heat really well. So we can use them actually far from the coil, so in bottom layers, and they're going to heat very well. At the same time, we have found that this type of tire fibers, when we use it in the surface, they tend to leave some emerging spikes from the surface that could compromise the safety of our road users. So for that reason, we also recommend to use them in bottom layers. On the contrary, steel wool and the shavings can be perfectly used in top layers. They heat very well when they're close to the induction coil, and they do not produce any kind of health or safety issues. Here I present very briefly the effect of aging in the asphalt and the effect of the content of RAP also in the asphalt. So as you can see, in general, more healing means more heating energy means more healing. The curves increase. But in general, as long as I increase the aging or the percentage of RAP in the mix, the healing is lower. So we cannot expect the same maximum healing, so the process is less effective. And at the same time, to obtain a certain healing, we need to apply more energy, which means that the process is also less efficient. Finally, just to talk about the fatigue results. What I present here in this graph is each point is a different sample where the healing was applied at a different number of cycles during the fatigue test. So in this case, I apply the healing at this number of cycles and I obtain this healing. If I apply the healing a bit later, the healing is better, and then goes down again. So for all the mixes, we have these bell-shaped curves, which have also an explanation, and is that if I apply the healing too soon, basically I have nothing to heal. I have no cracks, so the healing is nothing. But if I apply the healing also too late, the cracks are so wide that I cannot heal them either. So there is also an optimum time in the fatigue life or in the service life of a road where the healing is most effective. What I'm presenting here is different samples with different air voids content. So these are dense mixes. This is 5% of air voids, while these are very porous asphalt, something like 26%. So we can see a couple of things here. Is like, first, dense mixes cannot be healed as well as porous asphalt. Actually, the maximum healing here is something like 30%, the extension of service life, while for porous, we are reaching extension of 200%, which is very good. But this also comes with an inconvenience, is that I extend more the service life here, but also I need the optimum is sooner. So I need to apply more healing treatments. All right. At the same time, we can also see a couple of very interesting things, and is that for dense mixes, as soon as I move a bit from the optimum, results fall down quite sharply, and at the same time, it's not just that I fall down, they get negative, which means that the samples actually last less if I heat them than if I don't do anything. At the same time, porous asphalt, that does not happen, and as I said, we are reaching healing indices of more than 200%, which means they are higher than 100%. So 100% will be expectable if we heal the cracks and I have just a new sample. But instead of that, we are having a sample that lasts twice. So actually I have a better material when I heat it. So in order to try to give an explanation for all this, we carry out different tests, more fundamental tests, that I present very briefly here the results. So this is the distribution of air voids in the thickness of the sample. So this is the top surface and this is the bottom surface. So this is dense mix and this is porous mix. And we are going to see the difference in behavior. So the blue line is the distribution of air voids when the sample is new. When we apply the optimal number of cycles when I should do the healing, the air voids practically have no change, more or less around 5%, as I said before. But after heating it, the air voids are practically zero, which means that the air voids now are full of bitumen. And that's very important. On porous mixes, we started with this air voids content, so it's something around 20, 25%. But after when we carry out the healing, the fatigue test, there is a densification. So the air voids have reduced. And then when I heat it, then the air voids have not reduced anymore. So this difference in behavior are very important. At the same time, I could see this is the results of thermal expansion, and we see how different samples with different air voids content expand when I increase the temperature. So when the mixes are dense, so very little air void content, the expansion is very high. They expand a lot, so at the same time, we have all the air voids full of bitumen, and then the sample starts expanding. So in porous asphalt, that does not happen. So this led us to the final conclusion that I will try to summarize in this very last slide. I will try to summarize all the findings that I was talking before. So this is the difference between the behavior of dense mixes and porous mixes. First of all, in dense mixes, we have a higher level of interlocking between aggregate particles. The packing is much better. So first of all, the cracks are more likely to happen through cracks than in between the cracks. So if that happens, these cracks are very difficult to heal. Of course, we can fill them with bitumen, but the final strength of this material is never going to be the same that the virgin aggregate. So that's a first characteristic of dense mixes. Then, when I heat it, the bitumen can flow through the cracks and we can fill the cracks. But as I said before, if the bitumen is aged or we have rub content in the mix, this flow is going to be worse, it's going to be more difficult. Then we have seen that if we just reach a steady state temperature and we overheat for a long time the sample, the gravity is going to drag down the bitumen, so new air voids are going to happen, especially in the top area of the sample. And if we overheat it in terms of too much temperature, what we're going to produce is that the flow of bitumen through cracks, through this internal pore network, is going to exceed actually the flow capacity of this network. So as a consequence, we are going to create an internal pressure, and this is schematically what is going to happen inside the material. So the aggregates are going to separate. We're going to see actually an expansion of the material, as we could see in the previous slide. And when it cools down, actually the material is worse than before. And as a consequence, the service life of this material is going to be actually shorter than the initial material not heat. On the contrary, in porous asphalt, what we have is that, first of all, the weak points are this. So the cracks are more likely to happen in between the aggregates, so through the mastic. These cracks are very easy to heal. We just have to melt a bit the bitumen and they're going to heal. So this is going to be exactly what happens, and this is why porous asphalt is much easier to heal. As I said before, when we apply the loading cycles in a fatigue test, there is a densification. We could observe that. So when I reheat it, what I have is a sample that actually is better than new, because now it's denser, so it's going to resist more. And this is why we have healing indices that are actually higher than 100%. When I overheat it, so when the temperature is very high, the bitumen is going to expand, but the bitumen is plenty of space to expand. So in this case, the asphalt is not going to expand a lot, it's not going to expand at all, and so no damage will be produced. So basically, this is the difference in behaviors, and this is why porous asphalt is much easier and much more effective and efficient to heal. I hope that everything is clear. Otherwise, I will be very happy to answer your questions later. So thank you very much for your attention. And